so that's a good sign. And the author is Donald Perkins, Perkins, and it's an excellent overview introduction with it's sort of undergrad level. So it gives you the basic concepts of particle physics that you'll take with you as you go up and up to higher levels. And I'll take particle physics right through to PhD 2 level. So there are 4 more levels for particle physics. It's absolutely fundamental, right? So Perkins, right? Feynman's little book called simply QED, subtitle: The Strange Theory of Light and Matter. So it's just a little book, quite thin, about 150 pages. Okay, but it too, very clear. Feynman is a master at that. Very bright, extremely bright, well, genius. So by studying this book, you'll get a taste of what quantum field theory is about, and particularly quantum electrodynamics. I won't be teaching that in the proper course until M2, second year masters. Okay, so that will be an interesting introduction to the basic concepts of quantum field theory and quantum electrodynamics as an application. Now, the third book on knots, the author is Sosinsky, I think a Russian, Sossinsky, possibly Polish, not sure. The book's published by Harvard University Press. All 3 of these are available free on emule.com. So if you want them for free, you can just download them from Emule. But if you prefer hard copy, a lot of people do, you can get them secondhand on Amazon.com. So it's your choice. And this book gives you, just like the popular book by Feynman on QED, this is similar on the basic principles of knots, K-N-O-T-S, and goes in a sort of semi-popular hand-wavy way, but it introduces you to the main concepts of knot theory. And by the end of it, you have a pretty good overview of what knots are all about, getting up to the latest stuff. Like the last chapter in the book is knots and physics. So knot theory, how far will I go? Well, in terms of its links with topological quantum computing, and for that you need topological quantum field theory. So that's Witten's stuff. So that's way up there. That's PhD 2 level as well. So in a sense, indirectly, knot theory will go all the way through. But in terms of the mathematics of knots directly, I think probably M2 would take you there. So knots also important. So as you learn more topology, you will then be able to understand, say, M1, quasi M2 level knot theory, the mathematics of knot theory. Like, for example, you'll need concepts from M1 level algebraic topology on the fundamental group. If you don't know what I'm talking about, don't worry. But you'll need first year masters M1 level algebraic topology, the techniques, the tools from that subject, to apply them to M1 first year masters level knot theory. Alright, well, that's sort of an intro. Now, next lecture, the theory part, I've still to give the problem solving part of this lecture. But the theory part of next lecture, let's see, what's the label of the topic? I think it's just a... find it here. It's called, so chapter 10, and it's called just simply approximation methods, and with 3 parts. Perturbation theory, that's when you add a small term to the Hamiltonian, which implies corrections in the eigenfunctions, the eigenvalues. Okay, and then applications of perturbation theory, and then another mathematical technique called the variational method. And it's a fairly short chapter, just 9 pages. So this chapter we're just finishing now was 12, and the one after next is 10 pages, and that's the end of the course. Right? So I'm curious to see how many of you will be following my first computer theory on theory of computation course, because I know there are a lot more students out there of computer science than pure math or math physics. But I think that will change, because the future of computer science is mathematical physics, and the reason for that is, I will say this again in the future, I've said it in the past I guess, is that Moore's law, the driving force behind the computer industry, is scaling down the components of chips to such a point where quantum mechanics takes over. The phenomenon of quantum mechanics becomes important, and so quantum computing becomes inevitable. That has to be. And the future of quantum computing increasingly is a knowledge of math and physics. And to make quantum computers robust, so they resist the decoherence of noise, so local external factors interfere with the quantum states. And so to make those states robust, if you can manipulate quantum information, quantum bits or qubits, in topological quantum fields, which is PhD 2 level mathematics and physics, then maybe you can scale up. You can make large-scale quantum computers that are robust, they resist against noise, they don't lose their information. In other words, they do not decohere. And once that happens, quantum computers will just revolutionize everything, because they're exponentially more powerful than classical computers. And therefore you could simulate nature, you could simulate quantum systems, you could have artificial life in a computer, stuff like that. Just absolute revolution. And if that happens, then there will be jobs for mathematical physicists in the computing field. The computer scientists then will have to upgrade themselves to become mathematical physicists. The general status level of computer science will go up because it's become more quantum mechanics, and that's needed. That knowledge of topological quantum field theory and the like will be needed to understand modern or future modern quantum computers. So, and that's harder. Your average grad student in computer science today is not equal to your average pure math and mathematical physics student, but that will change as computer science becomes more mathematical physics. The standard will rise, and computer science status will rise correspondingly. And there will be jobs, lots of jobs, for experts with PhDs in computer science, with specialties as mathematical physics, right? So that they can then teach these principles to other grad students. There'll be a huge demand. There'll be teaching jobs at to teach grad students the principles of topological quantum computing and the like all over the planet. So lots of employment. So that will attract mathematical physicists to do quantum computing, and will attract the computer science people to do quantum computing, and especially topological quantum computing using topological quantum fields. So that I see as the future. And one of my several goals in these whole deGarisMPC courses is to teach you these principles, so that there will be jobs for you at the end of it. That's part of one of my goals. So, ciao.